Good afternoon and welcome to AICD class. So in this lecture, we will see some of the rapid simplification methods which will help us to analyze amplifier circuits, and we'll also get introduced to single stage amplifiers. So in the from the previous classes, from the last class, we developed the complete small signal model of the MOSFET, including the effects such as channel length modulation and body effect. So I hope you guys are familiar with the methods what I'm going to discuss now, and we named it as rapid simplification methods. You guys may be definitely familiar, but may not be with this title. That could be the only difference. All right, so we call this as rapid simplification methods because if we know these rapid simplification formulas, it is very easy to solve or to analyze the small signal equivalent circuit of amplifiers. That is a reason why we call them as rapid simplification methods. So as we discussed about MOSFET, uh, say if I am considering a single MOSFET like this, keeping the source terminal grounded and providing so for one thing here, all the circuits now what we consider here, all the MOSFETs, assume that the MOSFET is in saturation and sufficient voltages are applied to drain as well as gate. That is our assumption. Now my first question is, so for my questions you guys can ping in the chat box, a reply in the chat box here. My first question is, what is the impedance of this MOSFET when I look from what is the impedance? Even though it is impedance, I'm calling it as resistance. What is the impedance seen at the gate? So just to identify, this is gate, this is drain, and this is source. Very good. It is infinity. The resistance seen at the gate of any MOSFET is infinity. The reason is there is no gate current. Since there is no gate current, impedance being measured as voltage by current, and since the current is zero, your resistance is infinity. That is my first case. All right. So with this, if I go further, again, if I consider a MOSFET which is still in saturation, gate is suitably biased. Now my question is, what is the impedance seen from drain? What is the impedance seen from drain? Can I get a response in the chat box? Okay, then one, yeah. All right. So then I have to mention two cases here. First, I am considering this as ideal, where lambda is equal to 0. And second case, I am considering lambda not equal to 0. So both will give you two different values. If your lambda is equal to 0, then your impedance is equal to infinity. And if your lambda is not equal to 0, then your impedance is equal to R0. So looking at drain, the impedance seen is always R0, and that is what we actually see from the drain characteristics, right? So if you look at the cara, I know that ideally the cara is a straight line, something like this, right? Something like this. This is a straight line, that is why you have infinite resistance, but practically, including channel length modulation, the cara will have a shape of this, which is having a practical resistance, and we call it as R0, output resistance of the MOSFET. All right. Moving on, coming to the third combination, again a MOSFET, suitably biased, but drain and gate are shorted together in this fashion, and we are interested to know what is the resistance seen at the drain, which is all again drain and gate are shorted together here. Again, under two cases, first is lambda equal to 0, and the second case is lambda not equal to 0. Can I get answers in the chat box? What is the resistance when your lambda is equal to 0? When your lambda is equal to 0, when your lambda is equal to 0, the resistance is only 1 by Gm. But when it is not equal to 0, it is equal to 1 by Gm parallel to R0. I hope this is also clear for you guys, because these things you have already seen in your AMC, but this will become a major tool for us when we start discussing the various circuits in this course, the current course. Now moving on, bringing in one additional term here. Okay, one more combination I'll get here. Uh, looking at source. Looking at source, what is the impedance? Again, consider two cases, lambda equal to 0 and lambda not equal to 0. Looking at source, drain and gate are suitably connected to some potential. What will be your resistance when your lambda is equal to 0? It is 1 by gm. Yes, it is true. When your lambda is equal to 0, it is 1 by gm. And when your lambda is not equal to 0, it is 1 by gm parallel to R0. So one thing you can see, the resistance, yes, Anushka, yes, I'm looking at all the answers what you're posting in the chat box. So looking at source, the resistance looks like 1 by gm or 1 by gm parallel to R0, whichever, anyway, it is a smaller value. Looking at drain, when your drain and gate are shorted together also, the resistance is same. And this combination, when you have a resistance, drain and gate are shorted together, we call this as diode connected structure, because the MOSFET is no longer a 3-terminal device, but it looks like a 2-terminal device, because two terminals of MOSFET is shorted together. So this is called as a diode connected loop. Moving on with another combination. Yeah, so with another combination, I'm just drawing it in this fashion. Drain and gate are shorted together. I am looking at a resistance from source, but the difference is now I am bringing in the body terminal into picture, and body is connected to ground. Same as C, the case C, the third case, but here your body terminal is also coming into picture, and again here you can consider two cases. One is lambda equal to 0 and another case is lambda not equal to 0. Can I get answers from you guys? So the only difference now is, very good Avinash, it is 1 by gm plus gmb, that is true. Okay, now others will be wondering how it is 1 by gm plus gmb. Definitely we can derive that. There is no problem in deriving. But even before deriving, I would like you guys to just analyze and let me know what you are getting. I can do that analysis for you guys, but before that, okay, I'll do that analysis for you now. So we will come back after that. So what I have done here is I have taken the MOSFET, drain and gate are shorted together, and gate is connected to ground. Say this is shorted together to VDD, and this is the point where I want to know what is the resistance. So this is my question now. Now how will I solve this? I have to draw the equivalent circuit of the MOSFET, what I have obtained the other day. This is the equivalent circuit including body. So I will replace MOSFET first with the equivalent. So I have GM into VGS. Okay, so if I let me ask this question. So if you want to find the impedance at any port, what do you generally do? Can I get answers in the chat box? If I want to find impedance at this point, what is the general procedure to calculate impedance? Okay, I am explaining that here. The first thing is to connect a test voltage. We call it as V test. So the first step is to connect a test voltage, which can provide a test current. So I'll consider that I test is the current flowing. The current is I test, and to find resistance, what we do is we find V test by I test. This will tell you what is the impedance seen from this side. So ideally what we do is we connect a test to voltage, a voltage source, and we'll pump a current I test, and then we'll find what is V test by I test. That will give you the resistance. That is the idea, the general procedure to find the impedance. The same thing I'm applying here. Now, so the same principle, the same procedure I want to apply here, but at the same time I want to plug in the small signal equivalent circuit also. So one more thing I would like to remind you guys. So this point is VDD. So we know that for small signals DC, I'll just make a point that point here. For small signals, when we consider small AC signals, DC remains unchanged. Since it is not changing, we consider it as ground. You should understand the reason why we consider it as ground, because small signals or AC signals are changing. Since the DC signals are not changing, we are considering it there is zero change. There is no incremental change. There is no incremental difference. That is why we consider this VDD or supply voltages as ground. All right. So now what I do first is I'll just replace this with the small signal equivalent circuit of MOSFET, what we learned the other day. So this is GM this is R0, and one more current source here, which is called as GMB This is the equivalent circuit of MOSFET. Leaving this as your drain terminal, this as your gate, and this as your source terminal. This is the equivalent circuit of MOSFET. Now, how will I proceed with this? I have to do suitable changes to this, because you can see that I should connect a test voltage here, which is V test, and this current is I test. That is one thing. Second thing is drain and gate are shorted together, and they're both are connected to VDD. Now VDD is acting as ground, so this has to be grounded. Drain and gate are shorted together, and it is grounded. So I can do connection in this way also. Are you guys with me? Are you guys able to understand? Please respond in the chat box. Yeah, see, at any point, if you're not able to understand, please ping in the chat box. And if I'm not seeing your messages, please unmute and tell that, sir, can you repeat, or can you explain it once again? Okay, because whatever things I am explaining now, certain things I'm assuming that you know from your AMC, but still, if you are not aware, if you are not comfortable with that, please do let me know, and I'll explain that again. All right. So what I did is I replaced MOSFET with the equivalent circuit. Then I am making sufficient changes to that in order to find the output, the impedance at point, the impedance at source. Now these changes I made. Now one more thing I want to mention here. This is actually plus minus, and this plus minus is VGS voltage basically, right? But now I want to write a relationship between VGS and VTest, because ultimately what I want to find here is VTest by ITest. So if when you write certain expressions, and if that expressions contain only ITest and VTest, that will be very easy for us to analyze it further. All right. So what I do now is VTest is actually the voltage from source to ground. Now, how that is related to VGS? VGS is actually marked from ground to source. So I can say that VGS is equal to minus VTest, or if I apply a KVL here, I will understand that minus VGS minus Vtest is equal to 0. That will give you this formula. Vtest is equal to minus VGS. So why did I write this here? Because I want to write a KCL and get Vtest by Itest. So what I do now is I'll just apply. Okay, similarly, so VGS is equal to minus Vtest. Similarly, what is VBS? Let me look at this VBS also. VBS, what is VB? Body is connected to ground. You can see that body is connected to ground. So VBS is VB minus VS, which is equal to body is connected to ground minus what is VS? VS is connected to Vtest. In that way also I can say that VBS is equal to minus Vtest. The similar thing you can apply to VGS as well. VGS is equal to VG minus VS, where gate is connected to ground and VS is connected to a Vtest, right? So these are two takeaways, or these are two things we need to keep in mind. VGS is equal to minus Vtest and VBS is equal to minus Vtest. With this, you can go ahead and write the expression for Itest here. So you can see that Itest is the current in this direction, and there are currents coming in from the opposite direction, right? So what will I do now? I'll just take this. I'll take this to next page. All right. Now what will I do is right. So this is Itest. Now what are the currents in the opposite direction? So you can see that this node is, so the voltage across R0 is also Vtest, because R0 is connected between source and ground. So this voltage is plus, this is minus, so this is Vtest. Now if I look at the current direction, so the current is flowing in this direction for all this. So this is GM-VGS current, this is Vtest by R0 current, GMB-VBS current. These are the incoming currents, and this is Itest is flowing in this direction. So I can write that Itest is equal to GM-VGS plus GMB-VBS plus Vtest by R0, right? Or when I replace this VGS with Vtest, it is minus Vtest here, it is minus Vtest even here, plus Vtest by R0 equal to Itest. All right. Oh, I think I made a mistake here. 1 second, Itest.
Vtest by R0 would be other side of the equivalent.
Yes, all right. Yeah. Oh, yeah. So here the current is the plus minus, right? So current is in this direction, so it should be minus. Is that the only mistake I made? Yes. Is that right now? All
So
right.
for
Yes.
KCL,
Yeah.
shouldn't it be on the other side, the V test by
Yeah.
R?
Yes. 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 I made a mistake. Sorry. Yeah. Sum of all the currents to this point should be equal to 0, right? So I will write in this form: Itest plus GMVGS plus GMB-VBS. Now this is plus minus, so current is flowing in this direction. So minus Vtest by R0 is equal to 0. Is that right now? Sorry for making that mistake. this is the point. So I'm just writing all the sum of the currents to this node equal to 0, and one is away, and I just put a minus sign over there. All right. I hope all of you agree to this. And now I am just writing it as I test minus GM V test minus GMB V test minus V test by R naught is equal to 0. Or if I write V test, if I take V test to the other side, and if I do V test by I test, I can write as this as equal to, okay, let me do that also. For clarity, I test is equal to V test into GM plus GMB plus 1 by R naught. Or if I write V test by I test is equal to 1 by GM plus GMB plus 1 by R naught. All right. Or this can be further written as 1 by GM plus GMB parallel to R naught. All right. So we started our discussion here, and we had the same thing at point at as an example in C. There it is 1 by GM parallel to R naught, and now with lambda I got, sorry, without lambda I can say it is 1 by GM plus GMB, and with lambda it is 1 by GM plus GMB parallel to R naught. Now, even without doing this analysis, you can say this straightforward, because the only difference when we treat this body terminal here is we know that in the small signal equivalent circuit, you have one more current source adding in parallel. And since both VGS and VBS have the same voltage, the effect is, since there are two current sources in parallel, those two currents are getting added. Current sources are getting added, those currents are getting added, and you can simply put a GMB along with your GM. Right. I hope this is clear for you guys. I got the result as 1 by GM plus GMB parallel to R naught. And now, if your lambda is equal to 0, that means your R naught becomes infinity, and your resistance is only 1 by GM plus GMB. Resistance is only 1 by GM plus GMB in that case. All right. So now, as we when we move on to this question, so you can see that yeah. So for question number E, it is equal to 1 by GM plus GMB parallel to R naught. Are there any doubts, or it is clear? If you have questions, please ask.
Yes, sir.
Clear. All right. Thank you. No doubts. Thank you for that. Now we go for the last one. So here I do consider one transistor, and I say this resistance value is Rs, assuming that gate is suitably biased. Interested to know what is the resistance seen from here. Again, for two cases, one is lambda equal to 0, and the other one is lambda not equal to 0. Can I get answer from one of you? Let me check with Akash. Yes, are you there? Akash, yes.
Yes, sir.
Yeah, Akash, can you tell me what will be the resistance R looking at drain when there is a source resistance Rs without lambda? When your lambda is equal to 0. Or tell me when including lambda. Lambda not equal to 0, what is the value?
1 by GM
Hmm.
parallel R naught
Hmm.
whole plus RS.
Hmm. Okay, so you put 1 by GM parallel R naught by looking at the other, looking at C, you told it is 1 by GM parallel to R naught? No. My question is, why did you say it is 1 by GM parallel to R naught? Is it you compared with the other examples what we just saw, or you
Yes,
are
sir.
confused?
I'm confused. No, sir.
All
I
right.
think
Okay. Yeah.
it is R naught plus RS.
Yeah. So it is not R naught plus RS. There are some more additional terms. Okay, that is okay, Akash. You would have
It's R
forgot
naught
that.
plus RS plus GM R naught RS.
Yes, it is R naught plus RS plus GM R naught into RS. This is the expression. This definitely I remember. You would have derived this before. This is your resistance seen. Now my question is, this is something known for you. Now if I consider body terminal here as ground, that means if I
Then
am,
it will be R naught plus RS plus GMB R naught RS.
that is true, Amog. I think Amog, right?
Yes, sir.
Yeah, so gamma, if I'm considering body effect coefficient gamma not equal to 0, then your resistance will be equal to R naught plus RS plus GM plus GMB into R naught into RS. And also to say that when your lambda is equal to 0, all these things will becomes infinity, because you know that when your R naught is lambda is 0, R naught becomes infinity and your entire expression becomes infinity. All right. So these are some of the rapid simplification methods what we generally have as a tool in order to proceed with the small signal analysis of circuits. In this case, I haven't done the derivation including body effect, but I would recommend you guys to try that with the same example what I have performed here in the same way, but add a resistance R naught and just try it out. Okay, so tomorrow you should definitely try this on your notebook, and let us see what answers you are getting. Yeah, so if you have further doubts, you can hold on, or you can just put in the chat box. I'm just moving further and trying to explain you something about amplifiers. And we do generally call these amplifiers a single stage because we start with a single stage amplifier, and further we will develop on that. All right, so let me ask this question first. Why do we need amplifiers? Can I get response in the chat box? The need of amplifiers.
To reduce attenuation.
Yes, Amok. Yeah, so I would prefer you guys to use the chat box so that recording will not get disturbed. Yeah, to amplify signals. Many signals are very small. They need to be amplified to make it of practical use. Yes, strengthen the weak signal to reduce attenuation. Yes, that is even what Amog was sharing. Yeah. So in short, what I would say is amplifiers are needed for processing a signal processing, and even that can be to drive a load, drive a resistance. So you have a signal, but you need to drive another device, but the signal strength is very small. In that case, you will amplify it to drive a load. Or in some other cases, you may have a digital gate, and you need to provide sufficient input logic level to that gate, right? So in such case also we may need a previous circuit or a pre-amplifier where you need to do some amplification. So in that case also, I would say, even to provide a logic level to a digital gate, we may be in need of amplifiers, right? So amplifiers in general are used for processing a signal. So if I represent an amplifier with input, say I will write it as x of t and output as y of t. What I'm expecting is, if this is my input signal, which looks like very small, what I'm expecting is a signal of an larger magnitude or amplitude. That is what we meant by amplification, right? Now my question is, to do this, what should be this block, or whether this block should be linear or non-linear? I'm just bringing in one additional topic for discussion here. My question is, we are talking about amplifiers and we have a block as amplifier. Input signal is there and there is an output signal. Now my question is whether this block should be a linear block or a non-linear block. It can be a linear or a non-linear block. That is my question. All right, linear. So why would you say that this block should be linear? Any other answers? Kindly respond in chat box. Explain what do you mean by driving a load. Yes, Amitesh. Say for example, assume that you are in a public platform where you are using a microphone. You want to speak, and that should be listened by many people, right? So in a very simple way, driving a load is, say for example, you have a speaker with you, and you are speaking from here. This is your voice, say this is your voice, and now the speaker or this actuator should actually give you the speech signal at a larger amplitude. Now if I am directly giving this voice to the speaker, this voice is the intensity or the magnitude of the signal is very very weak, so that this cannot make any this cannot drive the speaker will not be driven, or the speaker cannot produce an output out of this small micro signal. Now even if you amplify this, it should be properly passed through several systems, and finally it should be actually given to an amplifier called as power amplifier, in order to have so that the signal will have sufficient power. When I say power, sufficient current to drive this load, or your actuator or your speaker will produce an output only if it is driven suitably. All right, so sufficient power should be delivered, then only your actuator will work. Yeah, that is the answer for Amitesh what you asked. Now Avinash, your question is yeah, thank you Amitesh. Linear as in dependency of output on input. Yeah, so what is your understanding? My question is whether this amplifier block can be linear or non-linear. So what do you understand by linearity? Linearity can be understood as simple as this. When there is a change in input, a corresponding change in the output, or output should change. Yeah, principle of superposition is applied. Yes. Or to make it clear in the context, why I asked it can be linear or not is just to ask, when you are providing a signal to an amplifier, what we expect from the amplifier is it should faithfully amplify the signal. When I say faithfully amplify, the meaning is the shape of the input signal, should be preserved. Shape of the input signal should be preserved. So that is possible only when yes, Amol. Yeah, that is true. Whatever you have written is correct. Now, when I say shape of the input signal can be preserved only when your system is linear. Will you agree to that? When I'm providing this shape input, I will get this shape output only if your system is linear. Because for whatever change at the input, output is also producing a proportional change with a scalar multiplication, of course, as Amog, as you have mentioned. Okay, or I'll just modify the question in this way. What will happen if this block is non-linear? What will happen if this block is non-linear? I told that if the system is linear, the signals will be faithfully amplified and the shape of the output signal will be preserved. Shape of the input signal will be preserved. Yes, very good, Amitesh. Yeah. So if at all there is a non-linearity, that can result in distortion. That can definitely result in distortion. Yes. All right. So then there are a lot of things to be discussed now. Okay. So I'll just bring in. Okay. But one more question. Let me ask. So I know that amplifier need to be linear, and if I know that if there is non-linearity, that will lead to distortion. So what is the meaning of that? I am providing a signal. The system is not linear. System is not providing output as such. So that means this can be a distortion. This can be considered as a distortion because I am trying to increase I wanted to increase my input amplitude by the process of amplification, but the system is non-linear, and in such case your output is actually getting clipped off. That is one kind of distortion, and that arises due to non-linearity, or it can either due to power supply limitation. Both cases it can come, but anyway, if your output shape is not preserved as your input, then we call it as the system is non-linear. One more thing to identify here is whatever devices we use inside to design an amplifier, we know that we definitely use some active devices. And you are familiar also with say for example RC coupled amplifier. You uses transistors, you may use BJTs, you may use MOSFETs, etc. Now my next question is whether these devices are linear devices or non-linear devices. Can I get some answers for this question? Whether the active devices like BJT, MOSFETs, whether they are linear devices or non-linear devices. Any answers for that? Non-linear. Very good, Avinash. Non-linear. How do you know that it is non-linear? Just by looking at the characteristics, we know that BJT, the current and the voltage is related in an exponential way, which is a non-linearity. Even in MOSFET, in the ideal case, we would say that MOSFET is a square law device because your current and voltage are related in terms of square. That is again a non-linearity, right? So all these active devices are non-linear. But then what we do? So we have nonlinear devices. Say this is V in and this is V out. And nonlinear devices will definitely give some nonlinear response. But what we do is we work on small linear segments of this nonlinear device. So we work on how do we get linear amplification out of a nonlinear device? Because we work on small linear segments of non-linear characteristics of a nonlinear device. I hope the statements what I'm making are making sense for you guys. So just concluding, just summarizing, amplifier should be linear in order to have faithful amplification, but we do have devices or components which shows non-linear nature. So if I use a non-linear device, definitely distortion or distortions can happen. But what we do generally is for small signal amplification, we do work on small linear segments of this non-linear cara of devices and thereby getting linear amplification. Right. To make it all right. So a BJT or MOSFET device is a non-linear, but a BJT amplifier MOSFET. Yes, yes, that is true. From the characteristics of both the devices, you can see that the cara is non-linear, but we are designing amplifiers out of BJT and MOSFETs, and we do have faithful amplification out of that. The meaning is then those amplifiers are working as linear amplifiers. So how do we achieve that? If you can remember, we would say something called as Q point or operating point, and we will also specify the input amplitude. So definitely you would have observed this in the lab. Even you had a 1 week lab. Even though you had a 1 week lab, you will definitely remember. Some of you will definitely remember when you were performing the experiment of RC coupled amplifier. You would have seen a distorted output, or you would have seen a clipped waveform when your input signal is very, very large. and the faculty or the teacher handled your class would have definitely told you you should use your input amplitude in this range, and we would have told you to keep your input amplitude from 20 millivolt to 50 millivolt, right? So we told you to keep the input as small as possible, and even before applying input we would also ask you to check the operating point or Q point. So why these things are ensured is just to make sure that we are working on small linear segments of the nonlinear Cara. All right. Yeah. So I was answering to Anushka's question because she asked whether these circuits are linear. Yes, we do operate them as linear, but in fact the circuits are non-linear. But by setting the operating point and by providing the appropriate input, we are working only on the linear segments of the nonlinear Cara. All right. So just to summarize what I told now in a mathematical fashion, we all know, or we can generally write y of t as alpha into x of t, just to say that the system is linear. But in reality, it is not at all linear. So in that case, what we do, we do take help of this expansion. We call it as Taylor series expansion, and we do write the terms like alpha naught plus alpha 1 x of t plus alpha 2 x square t plus alpha 3 x cube t plus etc. You may be wondering what I am writing here. I will just write this as plus higher order terms. Yeah. So what I was telling is, this is your, this is how we characterize non-linearity. So if a system is linear, I can directly write using this expression, but this shows a non-linear system, and this is generally characterized by the Taylor series expansion, what we are seeing now. Now, since I was mentioning what is x of t, x of t is your input signal, and your input signal is very, very small. Since your input is small, the x square t terms or x cube t terms or even higher order terms, all these higher order terms can be neglected. It is not that the terms are not there. Since your magnitude is in milli or micro and the square cubic terms will be still smaller, we are neglecting all those things, and we are approximating this expression as alpha naught plus alpha 1 x of t only. Now how will we understand this? If you look at this expression, this is output, this is your input signal, this is your gain, what we say as small signal gain, and this is your DC level or the operating point, output DC level. All right. I hope this made sense. If you have questions, you can ask. All right. So let me explain one more thing, and then I can open the forum for discussion. Going back to the MOSFET, a 3-terminal device. In fact, there is a 4th terminal, as we mentioned, G, D, and S. So now what do you mean by DC level? Yes, very good question. I will say DC level or DC term. Okay, so how will I explain that? Okay, just hold on. I'll explain this with a circuit now. All right. So DC level is nothing but your operating point or your your MOSFET. If you have a MOSFET, directly you cannot apply a small signal here. That small signal should definitely run on a particular DC level. Why? This DC only will make your MOSFET turn on, or you make your MOSFET in saturation. Yes, Amitesh, yes, definitely you will see that even in the drain current equation also. Yes. Okay, so what I was about to tell is your signal, since your signal is very, very small, signal cannot drive your MOSFET. For a MOSFET to be put in saturation, there should be sufficient DC, and that DC level or that DC term is what I marked here, but not at the input, but at the output. Even at the output, there will be a DC level, right? That DC level is what is mentioned, what is shown by alpha naught. I hope it is clear, Avinash and even others who asked that question. All right. So finally, coming to MOSFET, we know that if you want to use it as an amplifier, as we have seen here, amplifier will have there should be one input port, there should be one output port, and both input and output are connected with respect to a common reference terminal. So in that case, I would say there should be an input port, there should be an output port, and one common terminal. One common terminal. So one will act as input port with respect to a common terminal. Another terminal will act as output port with respect to a common terminal, and the third one will be common terminal, right? So in that fashion, we have three configurations or three ways we can configure MOSFET amplifiers. One is by keeping source as ground, by providing input to gate and output from drain. Since the source is common, we call this as common source amplifier, right? Similarly, now if you keep your drain terminal common, giving input to gate and output to output from source, since your drain is common, we call this as common drain. And finally, for this, we'll provide input to the source, output from drain, and if your gate is common, we call this as common gate, right? So one more thing you can observe, there are three terminals. So the body terminal is body terminal we will not consider for the amplifier configuration, because we know that body terminal is should be suitably biased. And in the beginning of our discussion of this ASCD class, I told that how your body terminal should be connected for your NMOS and PMOS, whether it should be connected to the highest potential or the least potential, depending on the type of MOSFET also. Now, for the three terminals, there are 6 different possible ways of configuring, but only these 3 are useful configurations, and we call it as common source, common drain, and common gate. Right. Now, one more thing. When I mention this as ground, and this also as ground terminal, the meaning is it is ground for the signal. Does not mean that always these common terminals should be connected to ground terminal. Right. So in your common source case, this will be almost always connected to ground. But in your other cases, drain, it is not connected to ground. It will be connected to DC voltage. As I mentioned before, for small signals, DC will be ground. That is why we call this as ground. Again, for your common gate, gate terminal can never be connected to ground. If it is not suitably biased, the transistor will not work. So when I mark it as ground, the meaning is it is signal ground. I hope this is clear. So I'll be winding up for today, but now I'll open for the questions if you have.